Hello, friends. Now we're going to get really into the method of Lagrange multipliers. So, first thing, we're going to be using this new variable, lambda. Lambda is a scalar. Lambda is going to be my Lagrange multiplier. All right, so before we utilize this, let's discuss some helpful theorems about why this method works. So the first theorem is the orthogonal gradient theorem, and it says given a multivariable function which is differentiable on a given region. And the interior of this surface contains a smooth curve, C. That C is the curve on the surface, and R is this vector function representing that curve. So if P naught is a point on the curve where F, the function, has a local max or min relative to any of the other values on the curve, then the gradient is orthogonal to the curve at the point. So now let's talk about why this is true. We're going to show that the gradient of F is orthogonal to the tangent vector, and the tangent vector would be r prime of t, evaluated at that point P naught. So if we think about the values of f on C, the function values on the curve are going to be given by x of t, y of t, and z of t, those components. And if I take the derivative of this function, we'll say that df, the derivative of f with respect to t, that's going to be the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt plus the partial of f with respect to z times dz dt. And we should easily be able to see this is the same as the gradient of f, those first three coefficients, dotted with the derivative of r. So at any P naught point where the function has a local max or min relative to its values on the curve, then we know that the gradient is going to be orthogonal to the curve at that point. And we have a corollary that goes along with this theorem. And the corollary says at all of the points on that smooth curve R, where a differentiable function f of xy takes on any local max or min relative to the values of the curve, then we can assume that the gradient dotted with the derivative of the vector representing the curve on the surface is going to equal 0. So we can just draw this assumption always. So now let's talk about the method and formally define the method for using Lagrange multipliers. Suppose we have a function f and g, both differentiable. The gradient of g is not 0, as long as the function g is organized such that it's equal to 0. If we want to find the local max and min values of a function f, subject to the g constraint, if they exist, we'll find the values of x, y, z, as well as this scalar multiple, a constant lambda, that satisfy these two equations simultaneously. So gradient of f equals lambda times the gradient of g, as well as that constraint function needs to be equal to 0. And what we have here is that we have defined this for 3 variables, x, y, and z, but all of these properties still apply for functions of 2 variables. It's similar, you just drop off that third z. All right, let's do our example. For this example, we're going to determine the greatest and the smallest values that this function f of xy equals xy can take or have, right? Greatest and smallest, max, min, we're optimizing. So the greatest and smallest values that the function f of xy equals x times y takes on the ellipse of x squared divided by 8 plus y squared divided by 2 equals 1. So we have our function. The function is f of xy equals that product xy. And my constraint is that we have to be on the ellipse when we're satisfying this max and min for the function. So g of xy equals x squared over 8 plus y squared over 2 minus 1. So we've got to make that equal to 0, which means I needed to move that constant over. So we are restricted as these maximum and minimum values need to occur on the ellipse. In order to solve this problem, we're going to use our method of Lagrange multipliers. And in order to do that, first we need the gradient of f and the gradient of g. So gradient for f is going to be yi plus xj, y being the partial with respect to x being the partial with respect to y. And the gradient for g, we'll take the derivative with respect to x. That's going to, or the partial derivative with respect to x, I should say it properly. I'm going to get x over 4, or 1/4 xi, plus 1 yj. So working through this and setting this up with my lambda equation, I know that yi plus xj equals lambda times the gradient of g, x over 4i plus yj. So that creates my system. I can see that y equals lambda over 4x and x equals lambda y. So we want to solve this system and see if we can determine what lambda is, as well as this x and y that would maximize or minimize the function. So let's see what we can get solving this system. I'm going to sub lambda over y in for my x value, and that gives me y equals lambda over 4 times lambda y, or rather y equals lambda over 4, lambda squared over 4y. Now, y is a variable, so we can't just divide by this variable because we don't know what it could be. It could be 0, right? And you're not allowed to divide by 0. So we have to think about what this means. So we have, we'll think about it this way. We've got y equals lambda squared over 4y. What does that mean? It means either y equals 0, or if it's not 0, then these y's have to be equal to each other, which would mean this would need to be a 1. And in order to make that a 1, lambda would be plus or minus 2. All right, so we're going to either have y equals 0 or lambda is equal to plus or minus 2. So we need to consider both cases. Case 1, we'll say if y equals 0. Well, if y equals 0, then that means x has to equal 0, because 0 times anything would give us 0. So if y equals 0, x equals 0. And that would give us this ordered pair 0, 0. But we have to be on the ellipse, and this is not possible on the ellipse. So we'll consider case 2. And that states, well, if y is not 0 and lambda is some positive or negative 2 value, we got plus or minus 2 for lambda. So what does this mean? Well, what we know up here is that x equals lambda over y. So if x equals positive or negative 2 over y, we have two equations to plug into our constraint. That's essentially what we're always going to do. So if we get down to solving for lambda, we're going to be looking at that value and plugging it into the constraint. And the constraint is we have x squared over 8 plus y squared over 2 equals 1. So if x is equal to this value, and I can do both at the same time because plugging a positive or negative in here is going to square that, I'm going to end up with 2y squared over 8 plus y squared over 2 equals 1. 4y squared over 8 plus y squared over 2 equals 1. So I have 1/2 plus 1/2, which is going to give me 1y squared equals 1. Solving that, I get y equals positive or negative 1. So my equation I'm using here, that's going to give me some different x values. So I've got x equals 2y. I have x equals negative 2y. I need to plug positive 1 and negative 1 into each of these equations. So 2 times positive 1 gives me 2. 2 times negative 1 gives me negative 2. Negative 2 times positive 1 gives me negative 2. Negative 2 times negative 1 gives me positive 2. And we now have 4 points of consideration for these critical values. So I took my two y's and I plugged my two y's into two equations. I got my 4 x's. Each y has a corresponding x. And evaluating all of these ordered pairs in my function, which is x times y, I get positive 2, negative 2, positive 2, and negative 2 as my outputs. So what is the largest value? My max is at positive 2, and the minimum is negative 2. So the way we could write our answer, therefore, the max is 2 at negative 2, negative 1, and positive 2, positive 1. And the minimum value is negative 2, occurring at 2 spots, 2, negative 1, and negative 2, positive 1. So let's think about visualizing this function as a set of level curves. So if we think about these level curves and these traces we would create here, we could have xy equal to a number of different values. Like this that I'm tracing in yellow looks to me like this would represent xy equal to 1, right? That curve there is xy equal 1, or rather y equals 1 over x. And what we have found is that we're going to maximize or minimize this function on this constraint where it's touching the ellipse for y equals 2 over x, which is this red function. And so you see there are these 1, 2, 3, 4 points if xy equals -2, we get this curve up here in the left and the right, lower right, top left. And then similarly, if xy is +2, we get this red curve, lower left, top right. And so what we're noticing is that these hyperbolas that just graze this ellipse and are actually tangent to the ellipse, that's where we have optimized our function. Okay, so we had all these different options and we solved to determine how to optimize the situation given the constraint that we had to be on that ellipse. And that concludes this presentation. Send me emails if you have any questions.